Okay, um, welcome to my YouTube channel. Hopefully, I keep uploading more videos. This is officially my first YouTube video on this channel, and I hope I get famous. I hope I get more followers, and I hope I keep uploading videos to this channel. So thank you, Ben, for like making us do something innovative. Yeah, so I hope you enjoy my presentation. Stay tuned or keep watching. So today I am really, really excited to tell you about what I do as a grad student and also show you how that is related to other things in the climate system. So vapor pressure deficit is a big part of my research. And for this project, I'm trying to see if there's a relationship between the vapor pressure deficit and the incoming surface solar radiation. So keep watching. Yep. So why did I pick this topic? I guess you already know. First is because my research is on VPD. It's a big part of my research. What I do is to compare different climate variables and create climate indices from them and see how those indices are showing drought differently across the globe. Recently, I created an index from the vapor pressure deficit, and I'm comparing that to another index to see how it's changing. So it's a big part of my research. I wanted something relevant to me, but also relevant to the purpose of this class. So VPD is very, very important with climate dynamics. First, because it takes into consideration so many things like the measure of water vapor, the measure of the atmospheric demand of the atmosphere, the measure of the atmospheric demand of water. So it also regulates plant water use, carbon and water cycles of ecosystems. So very, very important. I'm trying to hype what I do here, but very, very important for climate dynamics. So these are some of the objectives of all of the objectives of my project. The first is to tell you what BPD is and not just assume that you know what vapor pressure deficit is. And then I'll show you how relevant it is to the climate system, explore how it's changing in the USA, kind of show you how it's changing in the USA, and look at the relationship between BPD and solar radiation. So that's the big one for this project, right? To my knowledge, as someone who studies BPD a lot, I really haven't seen any study that tried to check for the relationship between BPD and solar radiation. A lot of times when I see things or papers on BPD, it's always on how temperature is causing BPD to increase or how BPD is affecting plant stress and drought. So I was curious. I was like, what's happening with solar radiation? Maybe other people know the answer. Maybe you know the answer, but I do not know the answer. So I wanted to explore that area. So what is VPD? It's a difference between the saturation vapor pressure and the actual vapor pressure. What is saturation vapor pressure? It's a measure of the maximum amount of water the atmosphere can hold at a given time. And for the actual vapor pressure, it's the measure of the actual water vapor in the atmosphere. So I kind of think about it as humans, there's a maximum capacity of water we can drink in a day, right? Maybe 5 liters, 10 liters, depending on your height and your weight. But most times we don't meet that capacity, right? We don't meet the maximum amount of water we can drink. So the actual water you drink in the day compared to the maximum amount of water you can drink in the day. It's kind of how you think about the VPD. So in the atmosphere, that's what the VPD is. It's the difference between ES and EA. So I'll be referring to ES as the saturation vapor pressure and the EA as the actual vapor pressure. Okay. So how does VPD represents the atmospheric demand for water? We know that saturation vapor pressure increases exponentially with temperature, right? When temperature is increasing, the atmosphere is also like very thirsty. And because of this, VPD is very sensitive to temperature. So because it's the difference between saturation vapor pressure and actual vapor pressure, it's very sensitive to temperature. We got that. Let's move on. So we know temperature increases suggests that there's also increase in VPD. Because as ES is increasing with temperature, what we don't know is if EA is also increasing at the same pace. So from class, we have actually seen that wet places will most likely get wetter and dry places will get drier. Um, but what we don't know is if um, temperature increasing at a place, um, also increasing saturation vapor pressure at that place. We don't know if those same regions will also have actual vapor pressure increasing at the same rates as saturation vapor pressure. And then that was why I bought this study from 2017 that showed the Colorado River. So from here, we can see the flow from the first time series. The second one is the precipitation trend and then temperature trend time series from 1906 to 2022. What we can see is that temperature is showing an increasing trend, but precipitation is showing more variability. And towards the end of the time series, you can see a decline. So one complexity about VPD is that we know saturation vapor pressure is increasing, but what we don't know is if actual vapor pressure is increasing at the same rate as ES at specific locations. And then this got me thinking about some questions I wanted to look at for this project. First, how is changes in ES and EA impacting VPD? Since EA is actually the measure of water vapor and ES increases with temperature, is there a relationship between VPD and solar radiation and also between ES, EA, and solar radiation? So that was what I was thinking about. Is there a relationship? Would there be a relationship? We'll find out as I go on. Okay, so let me tell you about my data and some of the analysis I did. So I got my data from ERA5. I can't remember the full meaning, but you can check that online. It's a high resolution reanalysis data, 0.1 degrees by 0.1 degrees from 1981 to 2020, because I wanted to see recent changes in my variables compared to historical changes. And I got temperature data, dew point temperature data, incoming surface solar radiation. I used the temperature data to get the saturation vapor pressure, the dew point temperature data to get the actual vapor pressure. Then the difference between both was used to get the vapor pressure deficit. So in a simple, I'm trying to make this as simple as possible, but yeah, this was my method. First, I used the Bolton 1980 method to calculate the saturation vapor pressure and the actual vapor pressure from temperature and dew point temperature respectively. And I got my VPD. Then I checked for the trend per decade to see how these different variables have been changing. So saturation vapor pressure, actual vapor pressure, and VPD. And then I used the 12-month moving average correlation to see the relationship between ES and solar radiation, EA and solar radiation, and VPD and solar radiation to see if I could find any relationship. I was really just curious and just trying to have fun. Okay, so these were my results. First, this is the saturation vapor pressure trend per decade, okay, from 1981 to 2020. And from here, the first thing that comes up is that there's actually an increasing trend in saturation vapor pressure, which makes sense because if temperature is increasing, then of course saturation vapor pressure is also increasing. So from about 0.2, most places are like from 0.2 to 1, and just few places in northern USA have like negative trend. Then I also look at EA. So I changed the color bar because ES is demand for water, EA is supply for water, and I wanted that to show in my color bar. So from here, we can see that there's also a trend, but we have more decreasing trend in EA compared to increasing trend when you look at the color bar, especially in the southwestern USA. The positive trend are like very, very little compared to like the negative trend. Or we have certain positive trend, but it's very little compared to what we have for ES. Then I check the trend for VPD, and of course, if ES is increasing more than EA is increasing, then this is accurate, or this actually shows us what we expect. VPD is showing a very, very positive trend or positive increase. Some parts of the Midwestern USA and Northern USA are actually showing some sort of little trend and negative trend. I think for the final project, what I'll have to do is to show the distinction between positive and negative. But from here, we can see that most part of the USA are showing increasing trend in VPD. So this is suggesting continental drying because VPD is the atmospheric demand for water. Okay, so then from this, we know that, okay, VPD is increasing due to temperature. Many studies have actually shown us that. Many studies have also shown that the impact of yeah, many studies have also shown the impact of BPD on plant stress and also solar radiation on plant stress. Like I've seen that over and over again from my research. But like I said earlier, what we don't know is if there's a relationship between solar radiation and BPD. Okay, so what's the relationship? Um, that was my question. What is there a relationship, and would the relationship look like in the USA from 1981 to 2020? So first I did a correlation of ES and solar radiation. And from here we can see that there's a positive relationship between ES and solar radiation. So it means as ES, saturation vapor pressure is increasing, solar radiation is most likely increasing. Then I checked for EA, and it's more of a negative correlation. Sorry, not trend. It's more of a negative relationship between EA and ES. So this means that EA is increasing, solar radiation is decreasing. And then I checked for VPD. VPD has the strongest positive relationship. So it means that the atmosphere is demanding more water, or as there's a higher atmospheric demand for water, then solar radiation increases, or incoming solar radiation increases. So VPD is increasing, SSRD is also increasing. So I decided to look at the maps. This is like the same result, but just with the map. And remember, this is moving correlation. So 12 months moving average correlation to actually show the different months. So I got monthly data, but I used the 12 months moving correlation. And from here, what we can see is like the same thing from here. We have mostly positive correlation between ES and incoming solar radiation. But with EA, it's a negative correlation. And then with VPD, it's very, very positive, high positive correlation with incoming solar radiation. So ES and EA, the take home from here is that ES and EA have opposite relationship with solar radiation. So when ES is increasing, solar radiation is increasing. But on the other hand, when EA is increasing, solar radiation is decreasing. And from the USA, what we can see is that from 1981 to 2020, the 12 months moving average correlation of BPD and solar radiation is actually very, very strong. So recently, you've been having more strong relationship between BPD and incoming solar radiation. So the thoughts on my results was, it got me thinking about a lot. So this is like very complex. Like I was trying to bring out the different aspects of vapor pressure deficit and kind of see how my results make sense. So the first thing I thought about was that yeah, I already talked about that. The results suggest that higher demand for water leads to decrease in incoming solar radiation, which makes sense, right? When I thought about the fact that okay, EA is the measure of water vapor, and since water vapor is a feedback, its relationship with solar radiation makes sense, right? But I wasn't sure if I was going to see that negative relationship because EA is not water vapor. It's a measure of water vapor. So I wanted to see if I would get that negative relationship. Another thing is that positive relationship with ES and VPD is less direct. Although this is like a correlation I did, I feel like the relationship is more complex. And what I thought about is that, okay, the positive correlation between ES and solar radiation could be because when there's like high atmospheric demand for water, you have less cloud formation. But also the relationship between VPD and cloud is like more complex, right? But when you have higher saturation vapor pressure, then I think it's you need more you need more water for humidity to be 100% for you to have cloud formation. So that was one explanation for having a strong relationship between ES and solar radiation. So when the maximum amount of water that the atmosphere can hold increases, then maybe cloud formation drops, and that allows more incoming solar radiation. So that was one thing I thought about, but it's not that it's like a complex process. It's not that easy, but those are the thoughts I have on my results. And then it got me thinking, okay, I can't just stop here, right? So for future research, I'm thinking of exploring this for my dissertation, making one of my dissertation topics. This actually gives us a little bit of what we want to see of the relationship between VPD and solar radiation. But I feel like it's not as easy as I made it look, right? Like, okay, it's just correlation. I feel like there are so many other things to look at. And another thing I thought about was to look at the different seasons. Okay, so how's the correlation between ES and solar radiation, EA, solar radiation, VPD, and solar radiation different from the winter and the summer? Of course, it's going to be different because solar radiation is lower during the winter compared to the summer, and these other variables are also like most likely lower during the winter compared to the summer. So those are some of the things I'll be doing for future research. For the purpose of this project, I think this is actually good enough. And then I would introduce cloud data. I've never worked with cloud data, but I'm going to introduce that to see if it has a relationship with saturation vapor pressure, and if that's the reason why we are having a strong correlation of saturation vapor pressure with solar radiation. And also, I'm open to suggestion. If you think you have an idea on how I can make this better for future research, things that should look like, I am really, really open to it. But yeah, this was my research. I was just very, very hyped about looking at this and checking for the relationship. And yeah, that's it. I hope you guys enjoyed this video. If you have questions or you have comments, you could drop them in the comments below. And also for the class, I know I'll be having a couple of reviews. So I'm open to your suggestions and any questions you have. But that's it. These are my references. Thank you for watching my first official YouTube video, and I hope you enjoyed it. So, yeah, have a great day.